The derivative. It's the fundamental idea in calculus from which everything else follows. If you've taken calculus, you probably remember all sorts of different formulas for taking the derivative. The power rule, the product rule, the quotient rule, and the chain rule. But before you could use any of these shortcuts, you had to learn the limit definition of the derivative, which usually starts out looking something like this. This is the derivative of a function at a point. Soon after, you learn the formal definition of the derivative given here. You probably also remember pulling out your hair due to the messy algebra that using this entails. It's kind of a rite of passage for all calculus students to go through this before learning the shortcuts. If you've taught calculus, you know that this can be a stumbling block for many students, both algebraically and conceptually. In this video, we're going to learn another definition of the derivative, which in many cases is much simpler algebraically and much more intuitive on a conceptual basis. And strangely enough, I've never seen it taught anywhere. First, let's review where this definition comes from. Here we have a graph of a function, y equals f of x, and a point on that graph that we'll just call x. Let's add a second point we'll call z, and we'll add a secant line between those 2 points. We'll indicate the rise and the run between the 2 points as delta y and delta x. The slope between those 2 points is defined as delta y over delta x, or the rise over the run. Delta y is f of z minus f of x, and delta x is just z minus x. In order to turn that secant line into a tangent line, we need to make delta x smaller and smaller. We do that by taking the limit as z approaches x. This gives us our first definition of the derivative. F prime of x is the limit as z approaches x of f of z minus f of x over z minus x. This is sometimes referred to as the alternative definition of the derivative, but it's really just a general form. Point z can be defined any way we like as long as it approaches x when we take the limit. The standard way to do this is to let z equal x plus h and allowing h to go to 0. Substituting this in, we can write delta y as f of x plus h minus f of x, while delta x is just h. We can now write the slope of the secant line as f of x plus h minus f of x over h. We want delta x to get smaller, so we take the limit as h approaches 0. Now we can write the standard definition of the derivative. F prime of x is the limit as h approaches 0 of f of x plus h minus f of x over h. But what if there was another way to let z approach x? Let's define z to be equal to tx. This ensures that the second point, tx, will always be a multiple of the first. If I change the value of this multiple t, we can see the second point move. And for a fixed value of t, when I change the value of x, both points move, but their ratio stays the same. Let's show the rise and the run and write them as delta y equals f of tx minus f of x, and delta x is tx minus x. Now we can write the slope of the secant line as f of tx minus f of x over tx minus x. To bring the 2 points together, instead of letting h approach 0, we let t approach 1. Now we can write the new definition of the derivative. F prime of x equals the limit as t approaches 1 of f of tx minus f of x over tx minus x. Let's compare the two different definitions of the derivative by taking the derivative of f of x equals x squared. Starting with the original definition, we have x plus h squared minus x squared over h. We expand the binomial, cancel x squareds, factor out an h on top, cancel the h, and finally we are free to plug in h equals 0, giving us a derivative of 2x. Now that was pretty straightforward, but notice that we didn't get the form of the derivative until the very end. Let's see what happens when we use the new definition. Plugging in f of x equals x squared, we get tx squared minus x squared over tx minus x. We distribute our exponent, And now we can factor out x squared out of the numerator and x out of the denominator. Moreover, we can pull those x's outside of the limit and simplify. What we've done is we've separated the problem into a factor that has x in it and a limit involving t only. Essentially, we already know the form of the derivative. The derivative of x squared must be proportional to x, where the constant of proportionality is whatever the value of the limit is. So let's evaluate the limit. We factor the numerator, cancel the t minus 1 factor, and we plug in 1 for t, giving us a constant of 2. So now we know the derivative is 2x. A little bit faster, a little bit simpler. Let's try a slightly trickier example. Let's take the derivative of the function f of x equals x cubed. Starting with the original definition, we have to expand x plus h to the third power. Now that can be kind of tricky if you multiply it out the long way, which is what a Calc 1 student might do. Of course, you can also use the binomial theorem to expand that out quickly. We cancel the x cubes, and now we factor out an h from all three terms on top. We cancel the h with the denominator, and now we're free to plug in h equals 0, finally arriving at the derivative 3x squared. A little bit more time intensive than before. Let's see if this is any easier using the new definition. Plugging in x cubed into our definition, we get tx cubed minus x cubed over tx minus x. We distribute the exponents, and like before, we can factor out the x's on top and the x's on the bottom. And again, we can pull it outside of the limit and simplify. This gives us the form of the derivative x squared. All we have to do now is find out what the limit is to get the constant. Factoring, we use difference of cubes, cancel out a t minus 1, and we plug in t equals 1, finally arriving at our derivative 3x squared. So we were able to get the form of the derivative in just a couple of easy steps, and then the rest of the problem was just finding the constant. Much easier than expanding out the binomial. Let's try a general example. Let's take the derivative of f of x equals x to the n. Essentially, we're going to prove the power rule for integer powers of n. Now, the standard proof that's taught using the original definition involves expanding x plus h to the n power. Now, the only way to do that is to use the binomial theorem. What we have is a polynomial starting with x to the n, but we don't know what n is, so we have to leave out a lot of terms in the ellipsis here. We can cancel x to the n's, and we can divide out one factor of h to get this expression. And we see that every term except for the first one has an h in it. When you let h go to 0, all those other terms disappear, and we're left with n x to the n minus 1. I learned that proof in high school, but it never seemed intuitive or obvious to me. Let's see if we can do better with the new definition. Plugging in f of x equals x to the n, we get tx to the n minus x to the n over tx minus x. We distribute our powers, and just like before, we can factor out the powers of x on top and the x on the bottom, and we can pull them outside of the limit, separating the problem. Simplifying outside, we get x to the n minus 1, and in just a couple of easy steps, we already know the form of the derivative, x to the n minus 1. The rest of the problem just involves simplifying this limit. In order to do this limit, we need to know how to factor t to the n minus 1. Now, by the time students are in Calc 1, they've learned factoring rules like difference of squares and difference of cubes, so factoring something like t squared minus 1 is easy. You get t minus 1 times t plus 1, or 1 plus t, and t cubed minus 1 factors as t minus 1 times 1 plus t squared. It's easy to learn this pattern, so we can see that t to the n minus 1 factors as t minus 1 times ascending powers of t, 1 plus t all the way up to t to the n minus 1 power. You can also prove this using synthetic division, so it's totally fair game for a Calc 1 class. Subbing this into our limit gives us this expression. Simplifying, we cancel the t minus 1's, and we see that every power of t has a coefficient of 1, so when I plug in 1, we just get a bunch of 1's that add up to n because there are n terms, and we have our derivative. Compared to the proof using the original definition, this proof is much easier, straightforward, and easy to follow. So why does this new definition of the derivative simplify so nicely for power functions? Here I have the function y equals x to the n and the points x and tx shown, along with their secant line. The vertical distance between these 2 points, delta y, is given as delta y equals tx to the n minus x to the n. But we can factor out that x to the n and get x to the n times t to the n minus 1. We see that delta y is always proportional to the original function x to the n. As I move x around, we can see delta y respond accordingly. The horizontal distance between these 2 points, delta x, is tx minus x, but we can factor out the x there as well, so that delta x equals x times t minus 1. And again, we see that the run is proportional to x itself. This means that the slope of this secant line, delta y over delta x, must always be proportional to x to the n minus 1. We can see how the slope changes as I move x around for a fixed value of t. This relationship holds as I let t approach 1. Taking the limit as t approaches 1, we can express delta y over delta x as n times x to the n minus 1. This gives a very intuitive basis for why power rule works. Now that we've seen why this new definition of the derivative works so well for power functions, let's apply it to a few more examples. Let's take the derivative of f of x equals square root of x. Using the original definition, we get the square root of x plus h minus the square root of x over h. Now this can be intimidating for a Calc 1 student the first time you've seen a problem like this, because it's not exactly clear where to go. Of course, the trick is just to multiply by the conjugate of the numerator in the numerator and denominator. This allows us to use difference of squares to multiply the numerators and get rid of those square roots. That just gives us x plus h minus x. Now we can cancel the x's in the numerator, cancel out the h's, and then we're finally free to plug in h equals 0, giving us 1 over 2 root x, which is our derivative. Let's see if using the new definition is any cleaner. We get the square root of tx minus the square root of x over tx minus x. We can split up that square root, and just as usual, we can factor out the x's in the numerator and the denominator and pull them outside of the limit, and then simplify. So in a couple of easy steps, we know the form of our derivative, 1 over the square root of x. Now to find that limit, we could use the conjugate trick again, but an even easier way is just to use a clever substitution. Let's let u equal the square root of t, which means that u squared equals t. As t approaches 1, u has to approach 1. Subbing those in, we get a new limit, which is pretty easy to factor. Cancel. We plug in 1 for u, and we know our coefficient is 1/2, giving us a derivative of 1 over 2 root x. Again, we get the form of the derivative right at the very start, and the problem is much easier and intuitive. Let's look at another common example. F of x equals 1 over x. Doing it the original way can be a bit cumbersome. We get a complex fraction, 1 over x plus h minus 1 over x all over h. In order to simplify this, we need to get a common denominator on top. That gives us x minus x plus h over x plus h times x, which is all over h. This needs to be cleaned up a little further. Let's put the h as a fraction on the side. And now we can distribute the negative, cancel the x's, cancel the factor of h. Finally, we can plug in h equals 0, giving us a derivative of negative 1 over x squared. Let's see if we can do any better with the new definition. Plugging in our function, we get 1 over tx minus 1 over x all over tx minus x. But I can use negative exponents instead of writing it as a fraction. Let's distribute that negative 1 exponent, And as usual, I can factor out the x's in the numerator and the x in the denominator, and I can pull them outside of the limit and then simplify. Now we know the form of our derivative, 1 over x squared. Now evaluating the limit itself is pretty straightforward. We can just multiply by a t in the numerator and denominator, distribute, cancel the t's. We can factor out a negative out of that numerator, and now we see that the t minus 1's cancel, and I can plug in t equals 1. So we have a coefficient of -1, and again, our derivative is -1 over x squared. Again, we get the form of the derivative right away, and we avoid some of the messier algebra that comes up with using the first definition. This next example is really cool. Let's take the derivative of f of x is absolute value of x. Now, if we write out the original definition using this function, we get a really cumbersome expression. We get the absolute value of x plus h minus absolute value of x over h. The problem is that we don't know if x is positive or negative, or if h is positive or negative, so these absolute values are very difficult to deal with. In fact, we almost never do it this way. We usually just define absolute value of x in a piecewise manner. Absolute value of x is x when x is positive, and negative x when x is negative. Taking the derivative is actually pretty easy. You just have to take the derivative of both cases. So f prime of x is either 1 or -1, depending on the sign of x. But we usually just stop there. We don't really have a nice closed form expression for our derivative. Using the new definition, we get absolute value of tx minus absolute value of x over tx minus x. Now we can distribute the absolute value to both of those factors, t and x. Now we can factor out the absolute value of x on top and the x in the denominator, and as usual, we can pull those outside of the limit, and we've separated our problem. In fact, we pretty much already know the derivative right here. All we have to do is figure out what the limit is. Now, a key insight is that as t approaches 1, t has to get positive. So we can assume that t is greater than 0, which means that the absolute value of t is equal to t. Subbing that expression in, the limit becomes really easy. I just cancel a factor, and we get a value of 1, which means our derivative is absolute value of x over x. Think about what we just did. We took the derivative of absolute value of x algebraically and got a closed form solution without ever having to use the piecewise definition. I've never seen that before prior to using this definition of the derivative. This next example is my favorite. Let's take the derivative of f of x equals natural log of x. Now, if I use the original definition, we get natural log of x plus h minus natural log of x over h. Now, for a Calc 1 student, this limit's actually pretty difficult. It is doable, but we usually don't do it this way. In fact, the derivative of natural log of x usually isn't even taught until students have learned how to take the derivative of an inverse function using this formula. The derivative of f inverse of x is the reciprocal of the derivative of f applied to f inverse of x. Let's see how this works using f of x equals e to the x, whose derivative is also e to the x, and whose inverse function is natural log of x. Plugging this all in, we get the derivative of ln of x is 1 over e to the ln of x power, which of course simplifies to 1 over x. Now that's fine, but it's not very intuitive. It would be a lot nicer if we could take the derivative of natural log of x using a fundamental definition. Trying it the new way, we get natural log of tx minus natural log of x over tx minus x. Now watch how beautifully this simplifies. We can distribute the natural log using log rules and get natural log of t plus natural log of x minus ln of x over tx minus x. Of course, we can cancel the natural log of x's on top, and I can factor out the x from the denominator, and we've separated the problem. 1 over x times this limit, so we know the form of our derivative is 1 over x. All we have to do now is evaluate that limit, and that takes a couple of steps. We're going to use a couple of clever substitutions to help us out. Let's clean up that denominator by letting u equal t minus 1. which means t equals 1 plus u. And as t approaches 1, u has to approach 0. Subbing these in, we change our limit. Let's rearrange and put the 1 over u out in front. And again, we can use log properties to bring that 1 over u up. Now this is starting to look a little bit familiar, but let's make another substitution to make this really clear. We want u to approach 0. That means that its reciprocal must approach infinity. So if we let u equal 1 over n, which means n equals 1 over u, as n approaches infinity, u will approach 0. Subbing these in, I get an even more recognizable form. The limit of the log is equal to the log of the limit, so I can put the limit inside the natural log. And now I get an expression that everyone should recognize. This is the definition of e. So we get the natural log of e, which is 1. And now we know our derivative is 1 over x. Think about what we did. We got the derivative of natural log of x to within a constant in about 3 simple steps. And we found the derivative without referencing inverse functions or knowing anything about the derivative of e to the x itself. Very cool. I thought I'd finish up this video with a couple of caveats. You may have noticed that this definition fails when x equals 0. If you plug in 0, you get f of 0 minus f of 0 over 0 minus 0, which is of course not defined. Luckily, there's an easy fix for this. If you want to take the derivative at x equals 0, you simply use the definition in the exact same way we've been using it, but put limit as x approaches 0 in front. This is really more of a theoretical concern rather than a practical one. Usually, that x in the denominator cancels out, and if it doesn't, that just means the limit wasn't defined as 0 anyway. So you don't really have to do anything differently. Also, this definition isn't foolproof. It doesn't work well in all situations. Applying it to something like e to the x doesn't give you something that's easy to work with. The old definition works better. Or if I try a trig function like sin x, same thing. There's really no easy way to simplify this, so you're better off with the original definition. Obviously, the more complicated the function gets, something like this, you wouldn't really want to use this definition or the old definition because they're both cumbersome. At this point, you'd be using chain rule or quotient rule or something like that. And lastly, while I did come up with this definition myself, I did find it strange that I've never seen this before. Sure enough, while making this video, I came across something called quantum calculus and the Q derivative, which was developed by Frank Hilton Jackson in the early 20th century and has its roots going back to Euler. As you can see, the definition of the Q derivative is f of qx minus f of x over qx minus x, almost identical to the form that I've been using. The difference is, with the Q derivative, you don't take the limit as q approaches 1. You leave it the way it is in this finite difference form. So maybe I was scooped by about a century, but I find it very surprising that this new definition isn't taught in a Calc 1 class given all its advantages. Well, that's it. I hope you found this new definition interesting. I'm very curious to hear from Calc 1 teachers. Is this something that you would introduce in your class alongside the original definition, even if just used as a teaching tool for understanding the power rule intuitively? Let me know in the comments. Thanks for watching. Please like and subscribe, and have a great day.